so sorry for interruption. Okay, so our discussion was, although we know the constantness or conservation of some of electron and hole fluxes, however, still this number is left as an unknown number. For example, if we have a certain number, yes, we can find another number to match the conservation. And if we have another number like 110, then still we have a number matching the current conservation. So this is not determined at all. So please read this line. Now let us assume that although there is no specific reason right now, but let me just assume that this arrow equal to also this field arrow. Then you can immediately find out the value. Say this is 30, say this is 100, then this is copied into 100 as our assumption, then sum of these two components becomes just 130. So simply speaking, if we have, for example, here 30, then this is just copied into here due to our assumption that current or flux is constant for each carrier type across this space charge region. Then we can achieve the value of these fluxes. Natural question is, how can we justify such kind of constantness? Why we say flux at this point and flux at this point can be a conserved quantity? The answer is, this assumption is not valid. This assumption is wrong. We have applied a wrong approximation, so we must improve it later. But if we once assume this kind of thing, then actually we can consider these fluxes. Yes, so we can calculate the fluxes. Then under such an assumption, once again, what is this assumption? Simply speaking, for electrons in the space charge region, we have no SRH recombination. Once we don't have no SRH recombination, then electron current density is conserved. Also, hole current density is conserved. Oh, then it sounds really strange because in this problem we are fully considering SRH recombination in this quasi-neutral n-type region, and also considering this SRH recombination in this quasi-neutral p-type region, and only at space charge region we neglect that component. Sounds really weird. How can you selectively, okay, I will turn off this SRH, only this part, and turn on, let's go. Now that is the situation. So it's not that rigorous at all. However, anyway, under such an assumption, then we can write down in this way. Please read this line. The total current flowing through PN diode is the sum of electron current density on the P side and hole current density on the N side. It means that, let me just write down once again, this is nothing but Jn evaluated at x sub p, and Jp evaluated at minus x sub n. By summing them all, we can calculate the current density. So in order to justify this one, actually we must say that Jp evaluated at x sub p equal to that one evaluated at original point, or also we have to have Jn evaluated at the quasi-neutral n-time region should be equal to the starting point of quasi-neutral p-type region. Only under this assumption we can make the diode current as a sum of what? Sum of electron contribution and hole contribution. So are you with me? So this diode current is constant all over our system. However, if we ask ourselves what is the portion of electron contribution to the total current, then it really depends on the position. For example, if we ask this question, how much the electron part contribute to the total current density, then the answer would be 100%. Then at this point, how much the electron current density contribute to the total current density, the answer would be almost 0. And in between, there will be change of a relative portion of electron contribution. So that is the situation we have assumed. So are you all with me? Please try to understand the continuity. Once again, it is easy to say that, easy to misunderstand that each species, like electrons and hole, should have current conservation, but this is not the case. In reality, we can say the overall conservation of sum of hole current and electron current. However, each current component, electron current density or hole current density, are not conserved in general case. So once you understand, please try to draw your figure 2.20 of Professor Tower's book. So please use this expression. So how can we have this tangent goes away? Because we are now assuming very long diode, WP and WN goes to infinity. So we can write down just in this form, and parameters are calculated following also the Professor Tower's book equation. Actually, there are many other models corresponding to this kind of mobility values, but you will find that actually, if you are working with a ticket simulator, actually you will find that this kind of values are implemented into your program. Actually, the data file you access actually takes this kind of values. Okay. By the way, if you are not specialized in this one, then don't worry. Then please take these values for your given value, and please try to draw IV characteristics. Now, before ending our lecture, once again, sorry for the interruption due to the false alarm, and we have to consider this final consideration about recombination. I mean that in order to obtain this form, diode current form, we had to introduce an assumption: continuity of each current density. Electron current density is constant, and hole current density is constant within the space charge region. Then when the recombination in the depletion is now newly added, then we can find the following relation. So simply speaking, still here my question is this net recombination occurs or net generation occurs in the forward bias mode? So in the forward bias mode, here we have net recombination. Then can you expect, for example, net generation in the same time? So I mean that in this PN junction at a given position, here we have a net recombination and here we have a net generation. It is difficult to say, so we will have also net recombination. But this sounds too, how can I say, quantitative. So if you really wanted to be a quantitative, then you have to understand this form. Your hole density, your electron density is given as Ni times exponential what? So here you have a thermal voltage and phi minus hole density. In this case, we have this form, and electron density Ni exponential plus thermal voltage phi minus phi n. So with these quasi-formal potentials, please try to make a product between these two. Then what will happen? If you just calculate n times p, then you will have just Ni square, and here you have additional factors. However, this phi related terms goes away because they are cancelled out, and the remaining thing is only the term like this, q over q, and you have positive phi p minus negative phi n. This is the product of your Pn everywhere. Everywhere, once you know phi p and phi n, you will get this product. Then please think about the case where your anode is forwardly biased, positively biased, and your cathode is just grounded. This is quite a typical case you are considering. In this case, please name the value, and please name the value. How large is it? Phi n, which is connected to your cathode, should be just 0, and phi p, which is connected to your anode, that should be V apply. Then what we can say is, in this slightly forward bias PN junction, our NP product is nothing but Ni square times exponential phi APP over cos KVT over Q. Yes, simply if you have a positive bias applied to your anode, then NP product is larger than squared Ni. So once again, it confirmed that even in this space charge region, we will have, once again, instead of a net generation, we will have a net recombination. So okay, I will stop here and continue the discussion in this Wednesday. Thank you.